Hello judges, my name is James Licato, and for my project I focused on designing a new composite material for use in water treatment to remove two toxic classes of micropollutants. Now these two toxic classes of micropollutants that I was looking at removing are pharmaceuticals and personal care products and perfluorinated alkyl substances. So pharmaceuticals and personal care products, or PPCPs, are products that we use every day, products and drugs, and through low metabolism and excretion, they end up in the environment because wastewater treatment facilities do not adequately remove them. Perfluorinated alkyl substances, or PFAS, otherwise known as forever chemicals, also end up in the environment because they are not adequately removed in wastewater treatment facilities. And they find their way into these plants through extensive use in consumer products. So PFAS are in many things that are non-stick, heat-resistant, water-resistant, stain-resistant, so things like Teflon, coatings on the inside of popcorn bags, the shiny coating on paper plates, coatings on carpets and rain jackets that are waterproof. All of those things contain PFAS. And PPCPs and PFAS, the reason why they're such a problem when they get into the environment is because they're actually toxic to many different aquatic organisms, and PFAS are even toxic to humans. So PPCPs can cause intersex, embryo mortality, and population decline in the environment, and PFAS can cause testicular and kidney cancer in humans, as well as being immunosuppressive, and they can cause a whole bunch of other diseases, some of which we don't even know about as of yet. So, my goal was to design a new wastewater treatment technology in the form of a zeolite composite material to remove these two classes of micropollutants from water. And the reason why I wanted to do this is because they're not adequately removed in water treatment. So how did I do this? Basically what I did is I used zeolites, which are microporous aluminosilicates. They have a symmetrical lattice structure on the molecular level, enabling them to act like nets, and they can trap these PPCPs and PFAS on the molecular level extremely effectively. And there are many variants. For my experiment, I used 6 different variants, which basically means 6 different types of nets. And to design a composite, the reason why I wanted to do this is because zeolites come in powdered form most of the time, and powders are not very applicable or practical in water treatment. So I designed a sand-like aggregate using sodium silicate, which is a binder, and these zeolite powders, and through a dehydration reaction in the lab, I was able to produce these sand-like particles. And to test these sand-like particles, I did 3 things. First, I tested it under controlled conditions using a mixture of 18 PPCPs and 3 PFAS. Then I tested it under real-world conditions using real wastewater treatment facility final effluent, so that water that comes out of the plant after being treated, from 3 wastewater treatment facilities, 1 in Maryland, 1 in DC, and 1 in Virginia. And the final thing that I did was I used mathematical adsorption isotherm modeling to determine several factors that would give me a better idea of how useful and applicable this zeolite composite would be in water treatment. These 2 factors that I tested were adsorption capacity and adsorption favorability. Adsorption capacity describes the amount that these zeolites are capable of absorbing, the amount of pollutants that is, and adsorption favorability basically speaks to the rate at which these composites are capable of removing these pollutants at the same time. So, there were 3 things that I concluded from my experimentation. The first thing was I found a need for new wastewater treatment technology in every single wastewater treatment facility that I sampled. I found between 44 and 58 PPCPs at every location, and I found 12 PFAS at every location, and several of these PPCPs and PFAS were at levels high enough to be causing a certain chronic hazard to aquatic species in that water. So I demonstrated a need for new technology as these plants were not adequately removing these pollutants. The second thing that I concluded was that my zeolite composite was capable of removing both PPCPs and PFAS under both controlled and real-world conditions. And the third thing that I concluded was that this zeolite composite that I designed can be directly added into existing wastewater treatment plant infrastructure. Because it is that sand-like aggregate, it can be directly added, and it really shows real promise in the future of water treatment. Thank you.